Good evening, ladies and gentlemen, and welcome to the SAIEE KwaZulu-Natal Centre webinar on hydrogen for a sustainable tomorrow. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel under the KZN Centre playlist. The QR code on your screen you can scan, and this will take you to register for the SAIEE TV channel. It is free to register. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you now to our host for tonight, Ms. Crystal Nagisha, who's the chairperson of the KZN Centre, and she's employed by eThekwini Electricity MV/LV Operations as a chief engineer and has served the organisation for the past 13 years with her involvement in various distribution automation projects and smart grid initiatives. Crystal holds a BSc Electronic Engineering degree from the University of KwaZulu-Natal and graduated with a Master of Business Administration degree from the University of Pretoria's Gordon Institute of Business Science. She's registered as a professional engineer with the Engineering Council of South Africa and an active member of SAIEE, serving on the SAIEE SA Women in Energy Net Zero Initiative work group, dealing with climate change impacts on the energy sector. I would then also like to add that on last Friday night at the SAIEE Annual Award, Crystal won the Engineering Excellence Award. Over to you, Crystal.
Thank you, Minx, and thank you for your kind words. It was a very successful gala, and well done to you and the team. Good afternoon, everyone, and thank you for joining us this evening for this exciting webinar. We encourage you as participants to share your questions at the end of the presentation. Today, I am joined by two experts in the industry who will be taking us through a discussion on green hydrogen. And as we all know, it's a very exciting and transformative topic in the field of sustainable energy. And the title of our presentation this evening is Green Hydrogen for a Sustainable Tomorrow, Evaluating the Financial and Technical Dimensions of Green Hydrogen Production in South Africa. I would now like to introduce you to our first speaker for this evening, Dr. Mohammed Faiz Khan. Dr. Khan received his BSc, MSc, and PhD degrees at the University of KwaZulu-Natal. He is currently employed as a senior lecturer in the discipline of electrical engineering at UKZN, with over 20 years of power utility experience before becoming an academic. He has a passion for power system innovations and developments that are implementable and can contribute positively to the industry and society. Dr. Khan is also a registered professional engineer with the Engineering Council of South Africa and a fellow of the SAIEE. And to note, Dr. Khan is also the vice chairman for the KZN Centre. I would now like to hand you over to Dr. Khan.
Thank you, Crystal. Can you see my screen?
Yes.
All right, excellent. Thank you for that wonderful introduction. I don't know whether I describe myself as an expert, but considering I'm giving the webinar, I'll just accept it for today, perhaps. I won't go through the entire presentation name because you've been through that, and it is quite a mouthful. But in essence, today we're going to be talking about green hydrogen and some rather technical aspects of it as well. But when I kind of started off on this topic and I decided to agree to supervise Umeshan, I didn't realize that I was going to be his opening act going forward whenever we talk about this topic. But it's a job that I'm happy to do because it's a topic that I'm sure all you guys are going to find really exciting. So to start, I'd like to perhaps go through the presentation outline for today. The questions are, why green hydrogen? So why are we talking about green hydrogen today? I thought hydrogen was colorless. That's my old academic attempt at humor. And then potential uses of green hydrogen. You hear the common theme that people ask, why are we taking renewable power and making hydrogen when we need all the renewable power to sort out the load shedding in ESCOM? We'll talk a bit about green hydrogen production in terms of electrolysis, etc., and then the green hydrogen economy, how it exists throughout the world, perhaps. Then I'll hand you over to Umeshan, who will go through an eThekwini case study, which is very relevant. And I don't think I'll say too much more about that because I think Umeshan covers it quite well. And then because I like to always have the last word, I will come back to kind of end the session off before we have the Q&A. So why is green hydrogen trending? Obviously, everybody knows most of the stuff. It's a growing demand for clean energy solutions, the shift towards decarbonization, and obviously advancements in technology and declining costs of renewable energy go hand in hand. We find that solar efficiency is getting better. We find that people are finding ways to make renewable energy more efficient. Hence the reason green hydrogen now is a buzzword almost. In the next slides, I'll kind of show you specifically why those things are important. But also the government policies that support green initiatives. They're growing not only in South Africa, but you'll see the example that I use for Japan later on in my slides, is something that kind of is saying, look, if we want to meet the climate targets by 2050, then we need to kind of consider very serious ways of decarbonizing our industry. So this is the hydrogen color spectrum. You'll notice at the top we have green and pink hydrogen, which is formed. Green hydrogen is green and pink hydrogen are the only greenhouse gas-friendly hydrogen production mechanisms. Currently, hydrogen is mainly produced primarily using coal or gas, which adds to the greenhouse gas emissions because it releases carbon dioxide as an output. Now, I think nuclear is something that needs to grow as well. So pink hydrogen is something that, in my opinion, deserves a lot more consideration as we plan for this new future and us attaining these targets in 2050. But for the sake of this conversation, we're going to be mainly talking about green hydrogen. And green hydrogen is effectively the production of hydrogen by the electrolysis of water, and the energy source has to be renewable. So the energy source is either wind, solar, hydro, geothermal, tidal. So you'll find throughout different countries, South Africa, for example, in the northern provinces, are mainly considering the solar advantage, whereas in some of the African countries, Central African countries that have water resources, they're looking at hydropower to create green hydrogen. Namibia, for example, is a big player in this market because they've got a lot of subsidies currently, and I think they plan their green hydrogen plan kind of overshadows us as South Africa right now. Now, we also have other colors, and the colors being blue, and as I said, mainly it's gray and brown that currently is being used. But blue hydrogen is something, to me, that's also quite exciting now. It's because everybody is so excited in this that people are now considering alternatives. Because there's, for example, this company in Finland now that's splitting methane into solid carbon and hydrogen using a process called methane pyrolysis. This is not something new because methane's always been split up to make hydrogen. But the difference here is that this is a CO2 emission-free option. So they basically don't add oxygen into the mix, and therefore no CO2 is created. So the carbon that is created is then used for nanotubes and other functions as well. But I digress. I think let's move back into the presentation today. I'm starting off by showing the United States energy mix. And the reason I'm showing it is to address the first question that I discussed when I talked about the outline. And that question was, why are we taking renewable power and using it to make green hydrogen rather than just providing energy? Now, this is the US energy mix. And you can see in the US energy mix, electricity basically makes up 25% of the energy mix, the rest being transportation, industry, etc. Now, in industry, there's certain industrial sectors like the manufacturing of steel, for example, that's really difficult to decarbonize using electricity. And therefore, that's where hydrogen comes in. So potential uses of green hydrogen, and perhaps that's where I'll discuss it further, is the decarbonizing of this heavy industry. So steel making, cement production, for example, you can now use the hydrogen directly as heat rather than electricity. And I think that's the reason why green steel is kind of also on the rise on the backs of green hydrogen. When we talk about transport, fuel cell vehicles, heavy transport, and aircraft. Now, aircraft is, for me, like the easiest example because it's very, very difficult to electrify an aircraft. To do so, you may need batteries that are heavier than the aircraft itself, if I could put it that way. So it just doesn't make any sort of feasible, viable sense. Therefore, this is where hydrogen is kind of playing a big part, although there are plans in place for heavy fuel cell vehicles like shipping and trucking, etc. as well. Then the chemical industry can be used in the production of ammonia, with key ingredients in fertilizers, for example. So these are the potential uses for green hydrogen. If we were to go back quickly, just to say, the idea, if you could see my mouse, is not to target this electric power, but to cut into the industry 23% and the transportation 28%. Transportation, we obviously have electric vehicles that's also helping out. So I think that's the reason why green hydrogen is making sense. Now, I started off with America, but now we can come back to South Africa, and I'll quote a very famous graphic that we see in a lot of presentations these days. It's from Stellenbosch University, from the Center for Renewable and Sustainable Energy Studies. And as you can see, we have a growth now in terms of concentrated solar power, we've got wind power, and we've got solar power. But of course, this is our electricity generation. And what we can't see is underneath this white line is a lot of brown. So in terms of renewable power, the reason why this graph is very different from the American graph is you'll find that in our energy mix, electricity still makes up a much bigger proportion of the energy mix as opposed to industry and transportation, because of how dependent, of course, we are on coal for our energy, or for our electricity rather. So in a nutshell, in a nice little tidy diagram, green hydrogen, as we discussed, we need renewable electricity generation, so either wind, solar, whatever, and that gets moved into a substation and then used in a hydrogen electrolyzer. So that's where water is basically split up into hydrogen and oxygen. Often a step in between here is where you have a desalination plant. As we know, water is a scarce commodity in South Africa. So any kind of hydrogen plant that we do have, for example, in eThekwini, will have to include desalination as well. So the electricity that's generated gets used in a desalination plant first, and then in the green hydrogen production. That's then distributed, and we'll talk about the hydrogen economy later. But in a nutshell, this is how green hydrogen is made. Now, when we talk about the green hydrogen economy, for me, we have to start with Japan, because in 2017, Japan became the first nation to implement a national hydrogen plan. And it's kind of obvious, it's born out of necessity, because Japan is limited in unused land, which means that Japan, unlike South Africa and other countries, they can't set up gigantic solar farms like those found in Australia and China and India to kind of decarbonize their grid or to kind of meet their carbon KPIs. So Japan is seeking to combine domestic technology for renewable energy derived hydrogen with an international supply chain for the gas itself. So they were one of the first countries who kind of already put on record, this is how much of green hydrogen we require as a country, and this is how much we're willing to pay for it. Over a quarter of the country's $20 billion Green Innovation Fund is allocated to hydrogen-related technologies. So they're betting very heavily on it. Cost remains a challenge to the adoption of green hydrogen. And to address that, and perhaps this is something that our government and other governments around the world need to kind of listen to, is that their government has launched a program that will subsidize buyers of green hydrogen for the next 15 years. That means any business purchasing a minimum of 3,000 metric tons of hydrogen per annum will pay no more for it than for natural gas. And that allows the technology to mature, it allows it to become more widespread, and with that, costs come further down. So that's a very nice initiative that the government there has kind of set up. Other countries around the world have similar initiatives, but we won't go through all of them in the interest of time. To talk about South Africa, South Africa's current vision is stated in the South African Hydrogen Society Roadmap, which was released in February 2022. Establishing a hydrogen economy for South Africa is seen as a tremendous opportunity to overhaul the country's industrial sector and also assist in achieving our targets for 2050. The other thing is that it ensures that the socio-economic inequality is also alleviated. You may have heard the term just energy transition, because I'm assuming people who are in this webinar are interested in such things. So green hydrogen is seen as one way. In fact, we are also currently writing a book chapter with the Human Sciences Research Council on green hydrogen, specifically looking at how the just energy transition can be assisted by going to green hydrogen rather than renewables only. So this roadmap establishes targets for the year 2050, but plans to implement 10 gigawatts of electrolysis in the northern regions of South Africa by 2030. Now, I know the cynics in the room are thinking, and perhaps those are the questions we're going to get later, but those targets seem lofty because let's face it, 2030 is now 5 years away. But at this point, I'm going to say, is it any more ambitious than us building 14,000 kilometers of transmission line in the next 10 years? My point here is not to belittle it or to say that we're not going to do either, but my point is, and I'll touch on it at the end of the presentation, is that we need to kind of have plans in place, and not only plans and documents and more reports, but we need to start executing on them. A report published by the National Business Initiative forecasts that South Africa, with its significant renewable potential, particularly in the northern provinces, could produce green hydrogen at a cost of $1.60 per kg, which is one of the lowest globally. So that's in terms of South Africa. So I think the South African projects that I'll just touch on briefly is that the Platinum Valley Initiative, I think, is the most famous one. It's the big corridor that links the mining activities in Limpopo all the way down to the port of Durban. Then we have the Coal CO2X project, which aims to utilize green hydrogen and captured pollutants from coal-fired boilers to generate value-added products such as green ammonia and fertilizers. Sustainable aviation fuels, I think we've spoken about that already. And I apologize if I don't pronounce this correctly, the Boegoebaai hub, which is in the Northern Cape. This is a nice example of a kind of a hub that looks at a lot of different interconnected industries in a way to kind of stimulate the economy, generate jobs in an area that doesn't have anything. And it's a large-scale industrial zone. It has 7 crucial facilities, but most important in the context of this presentation is an electrolyzer park, a green ammonia production plant, and a desalination plant. So South Africa have these plans, and perhaps I'll now kind of trail off. I warmed you up, hopefully, in terms of understanding what's green hydrogen and why we're doing it. We'll now kind of segue to Umesh's presentation, where we talk about an eThekwini case study. And the reason why we chose to look at this case study is obviously eThekwini forms part of that platinum corridor, but also in terms of the fact that when we're designing these things, we need to understand what we're doing, why we're doing it, and should we be doing it in the first place. And Umesh's study kind of answered a lot of those questions. I'm really grateful to the SAIEE to afford us this opportunity to present this research to you, because research like this doesn't just belong in a thesis or in a conference paper. It needs to be shared, discussed, and I feel only then can we have any chance of it being implemented. So with that, I'd like to perhaps hand over to Umesh, who will take you through the very technical details of his study, and I'll chat to you guys later. Thanks.
Thank you, Dr. Khan. I'd like to introduce Umesh Pillay to the audience. So Umesh Pillay is an electrical engineer with a diverse skill set encompassing various areas of expertise. His proficiencies include black start generation industrial energy audits, general industrial engineering, network modeling, renewable energy, medium voltage designs, arc flash studies, and MV protection coordination studies. Umesh demonstrates high analytical acumen and problem-solving abilities, allowing him to define complex issues and devise innovative solutions meticulously. In addition to his technical competencies, Umesh has an MSc in electrical engineering. His research is focused on the viability and technical challenges associated with the green hydrogen economy in the eThekwini corridor. Umesh is also employed by Zutari as an electrical engineer, and I'd like to hand you over to him now. Welcome, Umesh.
Hi, Crystal. Thanks for such an incredible introduction. Thank you, Dr. Khan, for building such a good platform as well. Please let me know if you guys can see my screen.
Umesh, I can't see your presentation as yet.
Okay.
Okay,
Crystal.
here we are. Yes,
Okay.
we're online.
All right, guys. So I'm not going to reintroduce the topic. I think it's been mentioned already.
Before you start, I think we're seeing your presenter view, not the slideshow.
Yeah. Yeah.
Okay.
Click there.
Okay.
Yeah, we're good now. Thanks.
All right. Okay. Thank you, Dr. Khan, for building such a good platform for me to extend on. As you said, I'd be taking us through some of the technicals of green hydrogen, and tomorrow is a public holiday, so let's get on with that really quick. Okay, so the aim of my study was to assess the viability of potential supplies in renewable power supply options for green hydrogen. As Dr. Khan mentioned, green hydrogen requires renewable energy, and to be honest, I thought I was a perfect person to do this study because I would have given you an unbiased opinion, because I don't really believe renewables is the way for the country. I'm a person that understands baseload is required, and yeah, and the only solutions to our energy crisis is nuclear. And I get shot down all the time for saying this, but that's the truth. So then we looked at evaluating the energy yields of the various supplies. So that's your megawatt hourage and what the facility required. We also looked at the instantaneous power of at different conditions. So that's very important, because you might have a solar facility that provides you your yield, but at certain times of the day you wouldn't get the instantaneous power. That means your hydrogen electrolyzers can't work. We looked at potential locations for the hydrogen production facility. We looked at the Port of Durban and the Kunubia industrial area. I think it was safe to say that we chose the Kunubia industrial area as a possible hydrogen hub. This was because of its large space availability to accommodate our renewable power supplies as well. Ideally, you want your power supplies close to the production plant to reduce your cable costs and typical engineer mindset of reducing costs. Also, currently in South Africa, we talk about the hydrogen economy. So if we have to produce hydrogen at the moment, we don't have hydrogen cars and uses for hydrogen. So our best bet is to export it. And Dubai Trade Port is so close to the Kunubia industrial zone. Hence, we did that. The Port of Durban was a better option, but there's like currently space constraints in the Port of Durban, and it's not a feasible option. Tidal flooding is also an issue, because the only available space at the Port of Durban is at the outskirts, and our equipment is relatively expensive, and we don't really want to see flood damage. I mean, we've seen the power of water recently with our heavy floods. Also, co-locating this hydrogen plant within the Kunubia industrial area allows us to use, as you'd see, oxygen is a byproduct. It allows us to utilize these waste streams and byproducts in a more effective way, as we could sell it as a offtake to the local industries in the area. Another thing is also beneficial, as Dr. Khan mentioned, the just energy transition. We could use these solar facilities as agrivoltaics to combine energy generation with agriculture by farming under canopies of solar panels within the same location. This allows us to create jobs as well. Okay, then we looked at financial analysis, looking at basic stuff, your NPVs, your return on your return on investments, your life cycle costing, your payback period. And then we looked at the results, and we proposed an hybrid solution. And this hybrid solution was just a proposal, and we looked at optimizing it. Okay, so the study locality and plant requirements. So I'm not sure if everyone knows that eThekwini was like one of the first municipalities to release a regional hydrogen strategy. And in this strategy, they looked at various, well, in our national hydrogen strategy, we have Cato Ridge, Richards Bay, and the Durban as the hydrogen corridors. So I chose to do my research based on Durban because I'm actually from Durban, so it made it easier. Durban was also one of the first municipalities to produce a regional hydrogen plan, and also the Durban port means, as I said before, the only possible use for hydrogen at the current moment is export, and I felt that would be the easiest. So I think for our plant, we had to look at industry benchmarks of what other plants are producing. We've seen that a typical plant produces like 2,000 kilograms of hydrogen a day. This fact actually scared me when I saw 20,000 liters of water required, and I was like, okay, I live in eThekwini, and when I open the tap when I get home, we do not have water. How are we going to do this? Then I realized there's something bigger in play here. So desalination is an option, and where we salt water is converted into normal water, and where we use wastewater recycling, so reverse osmosis to get water for the hydrogen electrolyzers. Based on this 2,000 kilograms and looking at typical electrolyzer sizing, we required a 15 MVA power supply. I'm sure like in industry, the industry guys will know 15 MVA is quite a big number. I think voltage levels, I chose to work at 11 kV because of the infrastructure available in the area. So I wanted to, the plan was, okay, later on you'd see that we have excess generation. So the closest substation there was 11 kV. So excess generation would have been sold as a byproduct. Also, we looked at harmonics. Harmonics is actually a big issue with these electrolyzers, as there's lots of power electronic equipment, and I think power electronics in any system leads to harmonics, and therefore we needed filters, active filters, to sort these issues out. Okay, let's look at photovoltaics as a potential power supply. So we all understand that PV doesn't function throughout the day. So in our study, we looked at operating our plant for 9 hours from 8 a.m. to 5 p.m., typical working day. For this, we saw we need 128.7 megawatt hours of energy a day, and this should be provided by the PV array. So the insulation factor for the Konobia area was 4.6 as per the GIS data sets we've used. This indicates there's 4.6 hours of optimal sunshine during the day. So one thing that really made me know I was on the right track. I'm not sure if you guys seen on LinkedIn and the recent eThekwini updates. So I was actually in a meeting with them, and ironically, we was talking about this 400 megawatts of generation they aim to install. So it's 100 megawatts of solar and 300 megawatts of gasification, I think. And ironically, this 100 megawatts of solar was in the same region that I have placed my solar farm during my study, so I knew I was on the right track there. Okay, as you see from the global horizontal radiation map, Durban is relatively green, so that's about 3.6 kilowatt hours per meter square of solar energy. But however, if you look at this in the grander scheme of things, like comparing it to countries like Germany and stuff, there's really no we really are ahead, and I'm sure everyone knows that Germany has some of the biggest solar facilities and stuff of that sort. So using our calculations and our typical engineering formula, I'm not going to bore everyone with, I think we size the plants to a 35 megawatt PV facility, and I think, yeah, we need 15 MVA, but there's a 35 megawatt PV plant. Okay, so here's the thing: we had to oversize the plant to get our energy required per day, which obviously adds cost to the project. Looking at the power generation, we'd require, so you'd see there's a distribution, and towards June, we lack power generated. That's okay because we're still above our threshold. However, the real issue is when you come to look at it on a daily, on an hourly limit. So you'd see there's lots of red areas during the day. So that's not acceptable because we want our facility to function full time to optimize the production and get our financial and our revenues out of the study. I mean, you don't want to be spending 800 million rand and not being able to use this plant for a good 3 hours a day. It just doesn't make sense financially. So the solution to this is BESS. BESS is quite expensive. Also, it increases your life cycle costing because these batteries are quite expensive. But then again, with BESS, you need to ask yourself. So this is where you ask the difficult questions, and people think it's really green. It's actually not. Lithium mining is really bad for the environment. Fair enough. Lots of people say PV is the way to go for green hydrogen, but as I said, I remain unbiased on PV because if you look at the actual cradle to grave of photovoltaics as a supply, you need to ask yourself, what happens to these panels after its lifespan? What happens to the batteries from the BESS after its lifespan? That's not accommodated. Everyone sees it as green now, but in the greater climate change scheme of things, I can guarantee you it's not. It's actually harmful to our environment. Lithium mining requires so much of water, and with water you get acid mine drainage issues and stuff. So it's an environmental concern, and green refers to the environment. So yeah, we just have to be careful with PV. So I'm very passionate about offshore wind, synchronous machines. So for any offshore facility to be viable, we require 6 meters per second of wind speed. As you could see, the coast of Durban, it's relatively red. I think it's about 9.4 meters per second. Looking at the wind index chart going throughout the year, it drops the wind speed in towards June, but that's the so the wind index is like a per unit value, so it's 1 of the average wind speed, so it'll be 0.9 times 9.4 meters per second, which is not a massive train smash, you know. We still can get the instantaneous power that we require. Okay, so here's the thing with wind. So based on the power curve, we see that we have a cut-in speed of about 4 meters per second, and we have 6. So looking at the power curve, extrapolating your points, you get a 5.5 megawatt hours of power per turbine. I think to fulfill our 4.3 megawatts, we require 4 turbines, but it's actually 3.1, and you're not going to. It's just safer to put 4 turbines as a contingency. So the as you can see, there's no issues with the instantaneous power. It's all over 14.3 megawatts. Perfect there, we're happy. But here's the issue. Okay, over generation. So if you look at the amount of power that we require per month, it's about 4,050 megawatt hours, but we producing on like our worst month about 11,000. That's almost 3 times the generation. Yeah, 3 times the generation required. So that's not good. So you have to ask yourself, what do we do here? So we looked at possible solutions. Okay, PV is under generating, offshore wind is over generating. I mean, one is doing what it's supposed to do, one is not doing what it's supposed to do. One is doing it better, one is there. So the way to do this is an hybrid solution. Okay, so that's our first solution, where we had a 35 megawatt solar farm tied to an LV collector, stepped up to 33 kV. general electrical engineering, step up to higher voltage to limit your power losses and assist with your voltage drops. We fed 2 renewable feeders at these plants. We actually have single line diagrams of these plants drawn out. Yeah, so 2 feeders, again, redundancy, and again with the same with the offshore wind farm. 32 megawatt offshore wind farm, 66 kVs. This is because your turbine, so ideally you want to transmit at your highest possible voltage within limits, you know. Then the same, fed into 2 renewable feeders. Remember, this is 2 different power supplies. Then we said, okay, let's look at combining an offshore facility with a solar facility. So the easiest way to do is let's take off the offshore wind farm and off the offshore off the solar facility, and we went on with our study like that. So we looked at the energy analysis. We saw that the hybrid solution continues to generate excess power from this graph, while 2 turbines deliver the required megawatt hours. You'd see they do not meet your instantaneous power. Remember, we need 14.3 megawatts of instantaneous power to run the plant. However, with 2 turbines, we're just getting 5.5 each, so that's 11. That doesn't make sense. So the hybrid approach offers a balanced solution, both financially and technically better than each other. But a quick question arises to us: what is the optimal contribution of wind and solar in the hybrid model? So that was really the part I enjoyed of the study the most. So yeah, so looking at our 3 initial solutions before we go on to our optimization, we see that hybrid is very balanced in your price, in your financial indicators. It's like we're looking at about 2 billion for a offshore wind, 800 million for a solar farm, and about 1.4 billion for a hybrid facility. As you can see, very balanced, very in the middle. Yeah, yellow. This is the key indicator lots of people look at, levelized cost of energy, which is very important. I think it's a good indicator to assess in financial analysis of power supply. So hence I did that. So hybrid optimization. So for any optimization, we need a optimization equation. Obviously, our aim was to optimize the number of the PV size and the number of turbines. So we looked at creating an optimization equation seen in equation 1. The optimizations are governed by constraints all the time. So as I said before, 14.3 megawatts of power required, monthly generated needs to be greater than 4,050 megawatt hours. And obviously for us to have an hybrid solution, our number of turbines need to be equal to be in between 1 and 4, and our PV facility needs to be in between 1 and 14.3. Hence it would not be hybrid. Because your solution will converge to a solution using an optimal amount of wind generation. So we use the meteoristic algorithms to solve this issue. So I looked at the genetic algorithm, particle swarm optimization, and flower pollination algorithm. So the reasons I chose this algorithms, I think I've written papers before and it fairly experienced in it, so it wasn't something new to me. So let's look at the genetic algorithm quickly. The genetic algorithm draws inspiration from the mechanism of natural selection. So Darwin's law there, survival of the fittest. Particle swarm optimization algorithm is considered an evolutionary algorithm. So this algorithm is based on the social behavior of organisms like birds and fish, and yeah, it involves the population of particles moving through a search space, adjusting its position, and then experiences and aiming to find optimal solutions to the optimization problem. Again, all this was done in Python, so we're not doing it manually. It's all scripts written, and that's how we solved it. So the flower pollination algorithm was also used to simulate the interactions between flowers and pollinators to iteratively search for an optimal solution to complex optimization problems. In the flower pollination algorithm, The potential solutions are represented as flowering plants, and the information exchange amongst flowers mimics the pollination with the morphid flowers influencing the population more strongly. Okay, so I think from optimization, we see that it's clear that we need a solar facility of like 24 megawatts coupled with like a 8 megawatt turbine. And yeah, that proved to work. I think because our algorithms converge to such similar values, we could say, okay, you know what, we're correct, and let's move forward in our study. Okay, this is just a graph to show you the power generated and the decrease. But remember, you know that story about we don't make decisions as engineers, so it's us finance guys, trust fund 65, blue eyes, it's them. So we had to do our financial analysis with that to see whether it's really been beneficial, because you see a decrease in power in the graph, but it's not drastic to actually merit the optimization, you know. So let's look at this. So we see initially capex reduction minus 21%, offshore. So why capex? Offshore wind farms are relatively expensive. The turbine technologies are hectically priced, so a reduction in the number of turbines significantly reduces the capex. Operational and maintenance saving, again, solely due to the wind farms. I mean, it's much easier to maintain a solar farm than a facility 21 k's in the ocean. I think the revenue in a revenue stream, we saw a lower revenue being produced, but this wasn't an issue because remember, the excess power was being sold to the eThekwini grid as a byproduct. So this was actually revenue from the municipality. So independent power producer, we served as an independent power producer selling energy. So this number really didn't affect us so much. The life cycle costing increases. All financial guys, we look at this life cycle costing, NPV positive. Our payback period decreased by 0.5 years. I mean, if you this is minus 4.2%, and this is actually quite good, because I mean, you want to get your money out of your investment as quick as you can. The return on investment 75%. If you compound this, it's relatively decent. And we saw a decrease in your levelized cost of energy, which, as I said, is a very important figure when you producing energy. Okay, so from our study, you could see that the algorithms performed consistently, converged on similar outputs. There's significant initial capex savings. There's energy optimization, minimized excess generation, balancing between potential and additional revenue, and the advantage of lower initial investments, and yeah, further financial benefits. I think I'd like to hand over to Dr. Khan to complete this webinar. Thank you to the SAIEE committee for having us here tonight. And yeah, I think it's because hydrogen is so new, it's good to share our knowledge on it.
Thank you, Mission. So the question now, I think that most of you may have stayed on for, is how do we get here? How do we get there, rather? And I know that Umesh and I may have like presented a case, but we tried to present a very balanced case. So I suppose some of you may even be asking the question, do we even want to go there? Part of the reason of this study was to kind of show the true cost of doing green hydrogen at eThekwini, where the solar insolation is quite low. We have similar studies being done in the Northern Cape, for example, and even in close to the Atlantic Ocean, to find, from a financial point of view, what makes the most sense. And the reason we want to do that is, and I didn't want to be outshone by my students, so I thought I'll also show some diagrams. But what this diagram shows is a very interesting study that was done. And what it shows is that in 2021, we have an announcement of green hydrogen. So here we look at 190 plants effectively in total. And in 2021, we had 4.28 gigawatts of green hydrogen being announced. Now, if you look at 2022, that number then drops to 2.6 gigawatts. Some of the projects disappeared completely, some of them were delayed, and the announcements in 2023, 1.01 gigawatts. So you can see as time is going by, although we have lots of announcements, what's actually ending up being constructed is a very small fraction of that, ultimately coming to 2024, where you only basically have 0.3 gigawatts of new capacity being installed and operational in 2023. This results in green hydrogen implementation gap of almost 4 gigawatts in 2023. And in trying to understand how we get there, I wanted to show this because this is showing kind of perhaps where we're going wrong. And I alluded to it earlier in my presentation where I spoke of perhaps not doing enough. Now, those of you who perhaps would have interacted with me in the past would know that I never leave a conversation without dropping at least one book reference. And I have to stress now for all of you present that I'm not getting any commission from Penguin Publishing. OKRs stand for Objectives and Key Results. Those of you all who know the Intel story will know that it was kind of used to great success at Intel when they used something called Operation Crush, which resulted in them having total dominance in the microcontroller industry in the 1980s, 1990s. And I believe that we need to now do the same with green hydrogen. And the key result that we aim for is cost. Now, John Dewar is a guy who was at Intel, and he wrote a book which is very good called Measure What Matters. But relevant to this is the second book that he wrote now called Speed and Scale, which is the book that uses OKRs and figures out how do we utilize OKRs to sort the climate crisis. Now, in this book, he proposes that the cost of producing green hydrogen drops from $2 per kg in 2030 to $1 per kg in 2040. Some of you will remember that earlier in my presentation, I said that South Africa has the potential to produce green hydrogen at $1.60, which kind of puts it in a very nice position here, considering this book. Now, this talking about climate change is a very nice segue into the next part of my next slide, actually, because this webinar was planned months ago, and it was serendipitous when the government announced earlier this week the signing of the Climate Change Act. So I thought it was a good time to share this information with you. It's welcome progress, in my opinion, and a clear indication that we are taking the risk posed by climate change very seriously. However, there are clauses that have been excluded, and I don't know whether that has to do with technological issues or issues with the GNU, but I'll leave the politics to another webcast. The challenge we have, though, is we have to bear in mind that this Climate Change Act also takes into account socioeconomic factors, costs, and the just energy transition. One clause that I don't claim to be a lawyer of any sort or somebody good with law, but something that kind of stood out for me was clause 24 here, which it says that the minister must, in consultation with cabinets, create a national greenhouse gas emission trajectory for the Republic. I personally can't see any sort of greenhouse gas emission trajectory that does not incorporate green hydrogen. To what extent, I'm not sure at the moment, but if we are going to meet our climate targets by 2050, this has to be part of the conversation. We've kind of shown our research. We've kind of discussed the plans that South Africa have, and we showed how in most countries those plans does not always come to fruition. So I think in closing, I need to say that we now need to change our focus. Our focus needs, and it's ironic coming from the fact that I'm saying this in a webinar, but we need to talk less. We need to talk less. We need to plan. I don't say plan less, but we've done all the planning. We've written lots of papers. If you look at the IEEE itself, the number of papers that were published in 2024 alone is staggering on the topic of green hydrogen. But we need to now start doing things. We need to start seeing, does it work? And kind of either fail fast and learn from our mistakes, or find out what's successful and kind of learn from that. And on that inspirational note, I'd like to thank you all for your time and attention this afternoon. Leaving with another literary quote, I believe that water will one day be used as a fuel that hydrogen and oxygen, which constitute it used alone or simultaneously, will provide an inexhaustible source of heat and light of an intensity that coal cannot have. I don't know, well, I can't unmute all of you, and I wonder whether any of you all know who this quote is from, but it's one of my favorite authors growing up. It's Jules Verne from The Mysterious Island, written in 1875. So perhaps he knew a lot more than we did, huh? And with that, I'd like to open it perhaps to Q&A. So Crystal, I'll hand over to you.
Thank you, Dr. Khan, and thank you, Umeshan, for that very insightful presentation. I'd like to encourage the participants to pop your questions into the question box, into the chat box. And we'd like to share these questions with our speakers this evening. Okay, so we've got a few coming through. Dr. Khan, I'm not sure if you're ready or who's going to be answering them, but I'm just going to pose it to both of you, Umeshan and Mohammed. So we've got one from Jamil Said, who's thank you for the engaging presentation that included the ROI. Umeshan, referring to slide 3 of your presentation. I'm not sure if you want to bring up slide 3, but what is the power source for desalination of the salt water?
Yeah, so Crystal, I think for the process to be green entirely and with the circular economy, so anything pertaining to green hydrogen needs to be green. So we would be using the offshore wind farm or the PV facility or hybrid facility as well. So yeah, I think with the circular economy, we also need our trucks and storage and your compressors, whatever items needs to be green. So you'd have hydrogen trucks. So you're not going to have fuel trucks because then you have some sort of emissions in this entire green process. Remember, the process of green hydrogen doesn't refer to the production of hydrogen alone from renewable sources, but it's creating that circular economy where everything is green. So yeah.
Okay, so there's a second part to the question. So if the plant needs coal-fired power stations, say to start, would it be feasible to switch to electricity generated from the hydrogen plant thereafter?
Yeah, I think, Crystal, that's we can't do that. It's not green. Emissions will be produced. I think with green hydrogen, there's no such thing as negligible emissions. It has to be zero. Because so there's something called yellow hydrogen, and a lot of countries actually produce hydrogen that is very close to green hydrogen. So it looks like the energy mix of the country. So like I think Iceland it is. They have so much of renewable energy that they produce hydrogen that is so close to green hydrogen. And I don't think there'd be an instance where you'd require coal fire to start up the facility.
If I can come in, Marshall, I think you're right. You're referring to that will be yellow hydrogen. So anything that includes anything else would be mixed origin.
Okay. Thanks for that. Dr. Khan, the next one is for you. So same speaker, audio, sorry, not speaker, but the question is coming from Jamil. How can I research progress at UKZN? I think this one's for you, Dr. Khan.
How can you research I'm assuming you're talking progress in terms of this?
The research progress at UKZN.
With regards to green hydrogen?
Yes.
I feel as if though perhaps in electrical engineering, at least, I may be the only one looking at it right now. So the short answer will be maybe my Google Scholar profile. But unfortunately, we are currently updating our webpage where we're going to have our research centers. So a lot of our papers that are being published will kind of come in there. So I think that's the best way to do it, to kind of perhaps join us on LinkedIn. There's a UKZN EECE fan club. And whenever we have presentations at conferences, whenever we publish journals at some of our good journals, to be honest, whenever we publish in any journal, we publish it there. So maybe on LinkedIn to look at the UKZN EECE fan club. Thanks, Crystal.
Okay, thanks, Dr. Khan. Our next question is from Paul de Villiers. Thank you for an interesting presentation. What is the approximate end-to-end efficiency for the conversion and utilization of hydrogen? And there's a second part to the question, which states, to what extent is this reduced by using seawater with desalination? So
Yeah,
I'm not
I'll
sure
come
who's
in there
going.
because
Yeah.
I think the answer is going to be that we really don't know at this point. Something that I should have maybe mentioned in my presentation, but I didn't want to sound too negative, is that when we kind of break down water to make hydrogen and oxygen, that's a very difficult, it's a very hard bond to break in the first place. So it's not a very efficient process of that. That's why the other concept of where we're breaking down methane to get the hydrogen is more energy efficient from that point of view. In our study, we didn't unfortunately calculate that to know that. So,
Yeah.
we looked at a lot of those processes as a black box, and because as an electrical engineering master's focused a lot on the electrical engineering costing and efficiencies.
Okay. Thanks for that, Dr. Khan. We have one more question by Cornelia Dladla. Thank you for the insightful presentation. I wanted to know, as in Japan, does South Africa offer any incentives or benefits for businesses using green hydrogen?
Yeah, Cornelia, I can handle that question. In terms of, it's a very valid question, and it's something that if I was to have a call to action, that's what I'd say. We need to have more of those kind of initiatives. So if you go through the entire Climate Act, you'll find that there are mechanisms that allow for those things to occur. And since it's only been signed in today, I suspect in the future, we're going to see a lot more of those initiatives come through. Because you have to realize that green hydrogen, it has the potential. When you look at merely renewable energy, that's the reason why we're having so much of challenges with the just energy transition. Because a just energy transition with renewable power by wind or solar, you're not adding any feed in. You're not trucking coal in. You're not putting coal into a conveyor belt. There's a lot of less people required. Whereas with green hydrogen, the plant itself, with pressured lines and gases, etc., it has the potential to kind of maintain some of those skills and jobs. So Cornelia, I think there's nothing currently in place in terms of as it is in Japan, but Japan was definitely kind of a front runner with that. My hope with this new Climate Change Act is that we're going to see similar kind of incentives in the future. Of course, things do change as well. I mean, I spoke about incentives, and there were lots of incentives that were brought in under the Biden administration, and we've seen them fall one by one in recent times. So let's hope that the politicians leave the energy issues to the engineers. Thanks.
Yeah.
Thanks, Dr. Khan. Umeshan, you wanted to come in there?
No, I'm good, Crystal. Thank you.
Okay. So we've got one more question. I'm going to take the last question now by Dr. Tony Mohandiwa. Considering production costs, infrastructure required in terms of hydrogen pipelines, trucks, etc., added to the desalination process, fire protection, how feasible is green hydrogen?
Yeah, so as Dr. Khan said, Crystal, this was an electrical engineering master's, and we've just focused on the power supply option of this. So remember, we said the levelized cost of energy, we didn't take into account your fire because that's going into like a typical consultant class 1 detailed design, and I don't think that's required at this stage. There's a lot of black boxes with an hydrogen. So if you look at your fire protection, there's no policies. There's such a lack of policies with regards to the protection, regards to the production of hydrogen. How do you know what fire equipment you need? There's no NFPA standard to say that as yet. With your piping, your ASTM standards it doesn't deal with hydrogen. Hydrogen is new. There's until we define policies and infrastructure. There are plans within eThekwini. You can. It's actually not. I would say the compressors and the storage is a major issue at the moment. They're only available overseas, but I mean you can get them here. It comes at a cost, but you can get them here. So green hydrogen, a lot of what we calculated is to see the ROI and stuff, but a lot of green hydrogen doesn't necessarily involve making profit or financial feasibility. I know I'm contradicting myself there. It's about creating that circular economy, which is green and interdependent on each other. So you producing hydrogen for trucking, and then we got aviation fuel. It's to create that micro circular economy interdependent of each other. So sometimes you need to leave the finances out and see how it actually functions, you know. Yeah, Dr. Khan, I don't know whether you want to come in there a bit more.
I think you're correct, Umesh, to say that we don't know the answers, and the reason we don't is it would depend very much on how the financier of this process, or whoever, for example, in Namibia or in Bukubai, they kind of very structuring their green hydrogen economy on the export market. So, their costing and the efficiencies will be based on that. But if you need to create your green hydrogen economy where you're kind of going to be utilizing the feedstock for yourself in industries next to you, that's a whole different ballgame. Now you're going to have to worry a lot more about safety. But the short answer is that without the policies in place and without knowing exactly what they're going to do, it's definitely something that needs to go in the basket of solutions. And there's very many ways in which it can be used. So it'll be very specific to how somebody wants to use it.
Correct. And remember, you can improve your financials significantly. Put an extra wind turbine at minimal cost, use the same network, generate much more energy. You cover your costs of your fire equipment, your infrastructure. So the byproducts as well, oxygen, sell it to your local residential areas. So you need to look at situations like that to recover it. I'll be honest, the whole front of green hydrogen looks negative, but we're never going to know if we never try. Okay, thank you.
Yeah, thanks to both of you, Dr. Khan and Umeshan. I think the audience has enjoyed this conversation. I think we need to have more of these conversations in our industry. Even as a country, I guess our economy rests on the sustainability of our energy security in the country. And I think as you dive deeper into these research and share it, I think it's going to be of great value to us in KZN and the rest of the country. So thank you to both of you, and I hope the audience has enjoyed these conversations. Please reach out to Dr. Khan and Umeshan. They have shared their contact details. For those of you that are still on, please look out for our handouts. We have the What Now magazine for those of you that are interested to download, and you can also, please, those that are not members of the SAIEE, you are welcome to participate in all of our lectures, webinars, events. Keep posted on our social media, on LinkedIn, Twitter, Facebook, and stay in touch. I hope you all have a good evening, and thank you for joining us.
Okay,
thank you,
everyone.
Thank you, Crystal. Thank you, everyone.